velocity field. So we assume that x is at a particular location, and we observe the signal for the one component of u. That means the x component of u. If I try to look at how the velocity field looks like, so in some particular flow, maybe I'm talking of a jet flow. So this is basically a jet coming out from a source. So let's say this is like a chimney from where flow is coming out, smoke or whatever airflow is coming out. So this is what we call as a jet flow, and at a particular, so this direction here is x1 or x. The downstream direction as the flow goes is what we call as the x1 or x direction, and u1 which I am going to write is the velocity along, or the component of velocity along the x1 direction. So we choose any one point, let us say some point here in this whole domain, I choose one point, and if I look at the velocity field in a turbulent flow, I'm just making some, the typical, I make measurements of velocity as a function of time, and this is how I will find the measurements. What will happen in a laminar flow? How will this velocity look like? It will be just a straight line, because at any one point the velocity will not change with time in a laminar flow. In a turbulent flow, you find these random fluctuating variations. Okay, so that is what you find in this. And so now here what one can do is one can calculate a mean velocity. I will come to a more technical definition of mean velocity maybe in the next lecture or the later. But here what I mean by mean velocity is I take an integral of u1 of t dt. That means, what does the integral represent? If I say integral of u1 of t dt, it will be the area under the curve. So now it is, the variable is dt. So I have to specify the limits of time. Okay, so I specify the limits of time as, let's say it starts from t1 and goes till some limit, some later time, t1 plus tau. So that means this distance, how much is this time gap? This is tau. I start from t1, go up to t1 plus tau. I take the area under the integral. So will that be the mean velocity? No. I have to divide it by the time interval. So this gives me the mean velocity, or it is actually a time average, what you say. So if I say this is equal to this, and we will use the symbol, this angled bracket for mean. There are two symbols used, one is an over bar and one is the angled bracket. Okay, we may use both, but so this is what we mean by, yes. Yeah, it's a function of x. It's a function of x. It won't be a function of t because you are integrating over time. So in fact, it turns out in this flow, it will be a function of x. It will be at x2 also, it will change with x2 also. If x2 is this horizontal direction, then the mean velocity at each x2 will also change. So here, that's why I'm taking only an integral on time. Okay, so I take an integral on time, that gives me the mean velocity. Now, if I plot the mean velocity here, mean velocity obviously will be constant, and this I can say will be the mean of u1, whatever the average value comes out to be. And obviously this is not a function of time, so this has to be constant. So this is the mean of u1. Now what one finds in turbulent flows, and again today's lecture will be mainly trying to tell you about turbulent flows. Okay, we'll not go into too much of maths. Those tools we will follow later in the course. So what we say is, whatever is this deviation from the mean at each time, the velocity is a function of time, mean velocity is not a function of time. But this quantity, this deviation, this is what we will call as the fluctuation from the mean. Okay, and this fluctuation, so if the velocity is u1, this will be equal to mean of u1 plus the fluctuation, and the fluctuation can be either plus or minus. So that is why I write it as plus fluctuation. Fluctuation can be negative also. In points where the velocity is below the mean velocity, the fluctuation will be obviously negative. Okay, so this is the velocity, and for the fluctuation, again either we will use small u1, this is one notation, small letter, or the traditional notation is, we call it as u1 prime. So prime is also used, or the small letter, depending on which book you follow. Particularly the two texts will be following, I'll give you a handout probably by next week, will be Pope's book and will be Lumley's book. So in one of the books they use a prime, in the other book they use this angled bracket and the small letter. So here sometimes, let me also put this, this is also used for mean quantity. I should, here it's velocity, so I say it could be mean temperature, it could be mean pressure. So we have this. Now what one sees is that typically the fluctuation is about the maximum value of fluctuation. So order of magnitude is about up to about a quarter of the mean velocity. It's not that the fluctuation is also equal to the mean velocity. It could be equal, but we find, that means what you find is that while there is a randomness in the turbulent flow, but there is also some sort of a sense of that it can't depart very much away from the mean. The flow tends to sort of vary. I won't say it's a periodic motion, obviously it is not, but it tends to move around the mean velocity itself with some ranges. So while there is disorder, but this disorder has a magnitude. It is not totally out of range of the mean. Yeah. No, this how much will the fluctuation be? Whether it's 25% or 5%, yeah, it will depend on the type of flows, but typically this is what I'm talking of. So I'm not talking real, I'm not even talking of, I just gave what flow it was, but this is just to introduce turbulence, that while we have a random flow, but that random flow is within some range of the mean. Now whether it is 20 or 25 or 30, it could vary. And you see, I'm talking of all these numbers 20, 25, 30 as if they are equal. And at least when we do order of magnitude analysis in turbulent flows, you'll find they will be equal. We will talk of order of magnitude like this, and that is one difference which is there in this course and the turbulence modeling course. In the modeling course, we only did the equations. We did the equations for turbulence modeling, which is probably what you need for your CFD simulations. But this course, being physics of turbulence, we will try to look into insights of what is happening in the turbulent flow. We'll also do some modeling. It's not that so some of that part you may find as a repetition, but I will do modeling because that is important for engineers and for other people. So we will do modeling, but this is just to. But then what one finds is that while in a turbulent flow, as we said, at every instant, each instant, the velocity goes like this in an apparently random way. But if I look at the mean velocity across x2, so let's say this is x1, x2 is the cross direction. Okay, there will be an x3 direction which will be perpendicular to the board. So I look at the mean velocity across x2, and what we find is, if I plot, now I do a non-dimensionalization x2 upon x1, and if I plot mean velocity divided by the mean velocity at the location. Now this mean velocity, as he rightly pointed out, is at a particular point. So for different values of x2, the mean velocity will be different. Where do you expect the mean velocity to be maximum for a given x1? At what value of x2? At x2 is equal to 0. At the center line, you will expect the velocity to be maximum, and then it trails out, and that is what we find, that even in the turbulent flow, this velocity graph, maybe the shape is not exactly the same, but it has this sort of a shape, and this shape, what we realize is, in this average velocity, we do not find any jaggedness. The average velocity as a function of x2 is a very smooth curve, and it changes in a smooth pattern. It does not change the way the turbulent velocity changed or the fluctuations changed. So that is what we are now will try to figure out by the end of this course, is that can we find some sort of, in the turbulent flow, what are the features which go like this. Now, one more thing which, in terms of numerical simulations, if you were to do a discretization for this field vis-a-vis the discretization for the second field, do you understand the meaning of discretization? If you don't, please ask. You don't, okay. Discretization means I have to solve the equations numerically. So I will be dividing my flow into domains. That is what I mean by discretization. So now the domain would be either a function of x or t, depending on what the variable is changing with. But here, if you want to capture these fluctuations, what can you say about the time step which you will have to take in the numerical simulations? Will it be small or will it be big? It has to be very small. It has to be of the order of somewhere where these variations are taking place with time. Only then you will be able to catch these velocity variations, because in a discretized domain you get velocity only at one point, then you get it at the next point, and you assume some sort of a variation between these two. So if your domain is very big, let's say your domain is of this size, of size t1, then you will only be able to capture some broad points, you will not be able to capture the variations. Whereas when you do a simulation for this mean field, now it is of course as a function of x2, not as a function of time. So here you can relatively take bigger compartments, because here the variations are not at a small scale. And that is, as you will realize, the biggest problem or the biggest challenge which we get in turbulent flows. That when even if we assume Navier-Stokes equations will give us the solution, if it's a turbulent flow, then you have to go to scales which are very small, which means your domain has to be very small and time domain has to be small. So you have to carry out many longer or many larger number of calculations. And this is what when you do turbulence modeling, then you say that I will only solve the equation for mean velocity. I will not solve for fluctuations at all. And then you are in a sort of a better state, that mean velocity is smooth, so you can have bigger domains. Okay? Does everybody see that? Again, it is being very heuristic, very qualitative, but that is what one does. So then why don't we just solve for the mean velocity? And there you will see, so that when we try to solve for the mean velocity, we encounter what is called the closure problem of turbulence. And again, has anyone heard of this term? Closure problem of turbulence. What do you understand by this, if you have heard or you just heard?
So, there are some models like K-epsilon model or
Yes.
So there is a closure problem.
No, but what exactly do you think the closure problem is?
Means equations
Yeah, right.
Equations are less and
Number of unknowns are more. Closure problem in any physical problem is when you have lesser number of equations and more variables. And we will see what we do is in turbulence, one of the first things we'll do is let us write the equation for mean velocity. Then what you will find is equation for mean velocity will contain some extra terms. By itself, the Navier-Stokes equations, you have, if you look at totally incompressible case, there are 3 velocity components, 1 pressure, and there are 4 equations, 3 Navier-Stokes equations, 3 components, and the continuity equation. 4 equations, 4 unknowns, so at least theoretically it is a closed problem. But once you take the mean, then what you realize, the mean equation will contain fluctuations. So then you say, okay, let's write the equation for the fluctuations. When you write the equation for the, either you solve the mean and fluctuation equations, but then fluctuation equations will require that we solve them at a very small scale, because fluctuations vary very rapidly and they are at very small scale. And it turns out that even with the best computers, for practical flows, we can't solve a full problem directly. Such an approach where we just solve the Navier-Stokes equation is called DNS, direct numerical simulation. But then we say we write the equation only for the mean velocity. But mean velocity will contain some fluctuating terms, which we will see, I think, by about the 3rd or the 4th lecture. And then we say we have to write the equation for those quantities. When we write the equation for those quantities, we encounter higher order terms. So, and the problem never gets closed, and that is why it is called closure problem of turbulence. And that occurs because our original equations are nonlinear. For a linear equation set, this will not happen. But because of the nonlinear term in turbulence, we get this. So again, this will follow. So now let's try to see some of the characteristics of turbulent flow. So the first thing we find is any turbulent signal, whether it is a velocity or a temperature, wherever there is turbulence, if we look at the dependent variable and we plot it, we find it is irregular or there is an element of randomness. So with this, there will be no deterministic approach with which equations can be easily solved. And hence, one has to resort to what are termed as statistical methods. And statistical methods, one of the simplest ways to find the mean velocity. Write the equation for mean velocity, try to solve for that. So this is what we mean by statistical methods in a very simple sense. Of course, a lot of turbulence theory which developed from 1950s till about 2000 was based on statistical methods, because that is the only analytical way in which you can solve turbulence. but we are restrained only to the averages, maybe higher order averages, not just mean of u. Maybe there's a fluctuating quantity multiplied by itself, that average and so on, but we are restrained to that. But I think a lot of shift came in late 90s till today, and that is that we are trying to solve these problems. Instead of an analytical approach, we try to take the numerical approach, trying to solve the equations from CFD perspective. And that is where then modeling started coming in. In fact, models started coming up from about 50 onwards. The first more complex models came in 70s, and then, but then the models also started becoming complicated. So then we use the term what is called as DNS. Again, I'm just introducing the term. We'll look at it later. Direct numerical simulations. And direct numerical simulation means you solve the Navier-Stokes as it is for all scales. That means you go to the smallest scale and solve the Navier-Stokes. So we are able to do it only for some very special cases. We call that homogeneous turbulence, and we don't solve them using the normal method which we do. Normally, if you have a differential equation, how do you solve it with a numerical technique? We use what? Finite difference or finite volume or finite element methods. One of these. And we do still use them for turbulence, but then most of the DNS problems in turbulence are solved using the spectral methods. That means you take a Fourier transform of the symbol, write the equations in the wave number domain instead of x, y, z. So therefore then everything will be converted to an ordinary differential equation for the coefficients. And you solve for those coefficients, which will be thousands in numbers, and then get the solution from those. That is what one does in DNS. And there is another approach which is in some sense a mixture of the modeling approach and the DNS, which is called LES. Does anyone know the full form? Large eddy simulation. So again, we will be looking at that later. I'm not going into that now. So large eddy simulation is another way where you treat the equations like you are doing in DNS, but you use a model and cut them off at some scale, so that you don't have to solve such a large number of equations. That is what you do in LES. So coming back to the physical properties of the turbulent flows, characteristics, and the first one which we talked of is irregularity or randomness. The second one, which we again looked at but yesterday, was in all turbulent flows, there is a very high diffusivity. What do we mean by diffusivity? Means mixing. Okay. Now, if we look at a typical heat transfer equation, only conduction equation. Conduction equation is what? Partial theta by partial t is equal to K divided by rho C times del square T. So in this equation, there is no velocity, it's only temperature. So there we have a constant K by rho C, which comes in front of del square T. And that is what we call as diffusivity, thermal diffusivity. So this K by rho C term is the one which tells how fast the temperature will diffuse. And we call it molecular diffusivity because there the diffusion is being done only by the fluid and its molecular properties. But in turbulent flows, what we find is that there is rapid mixing and there is high rate of momentum, heat, and mass transfer. And this is a very important characteristic because as this leads to enhanced rates of transfer. And the example could be, this could be heat, mass transfer. It could be a source of resistance in pipe flows. In normal pipe flows, where there's only viscous diffusion, there's a viscous stress. But there's enhanced rate of resistance in pipe flows with turbulent flows. And then another example is when we look at wind and ocean currents. There the mixing again is very high, and that is because of turbulence. Now all turbulence which we see, and this is essentially a large Reynolds number phenomenon. And as we saw in last class, when I talked of the famous experiment of Reynolds, where when the velocities were low, the flow was laminar, but as slowly the velocity was increased in the pipe, the flow started becoming turbulent. So therefore, often the turbulence starts as instability of laminar flow. Do we understand the meaning of stability? Stability means you have some solution and you perturb it. If the system comes back or is in close vicinity of the original solution, then the system is said to be stable. But if it goes away, then we say it is unstable. So in that sense, turbulence often occurs as that there is a laminar flow, you disturb it and then it becomes unstable and it becomes turbulence. So, and this happens because there is an interaction of viscous and non-linear terms in the Navier-Stokes equation. In general, if I say that turbulence is a large Reynolds number phenomena, then if you look at it in the Navier-Stokes equations, if I look at the non-dimensionalized form of the equations, then the equations look like rho times. Now this contains both the convective as well as the local term. I have put it total derivative is equal to minus grad P plus mu del square V. So this is the dimensional form, and the non-dimensional form becomes dV by dt is equal to minus gradient of P star, or maybe I can use V star here, plus 1 over Re del square of V star. So a cursorily look at this equation tends to make us believe that since there is a 1 over Re in front of the viscous term, and because there is the Navier-Stokes, there is a 1 over Re and it's a large Reynolds number phenomena. So the effect of viscosity should be very little and it should be maybe zero. But that is not so, because And this has to do with the nature of the equations. In fact, the boundary layer phenomena essentially comes because of this only, that there's a second order derivative. You need this term, even if the Reynolds number is very high. You can't throw away this term. And in turbulence, what happens is that there is a interaction between the nonlinear term and the viscous term, and that is what leads to, in some sense, the sustenance of turbulence. And again, more of this will follow as we do more things. Now, the next property which I'd like to talk about in turbulent flows is three-dimensional vorticity fluctuations. Again, this is a property of the turbulent flow that you find this in all turbulent flow. Now, do we all know what is vorticity? I'm sure you will not know. You have not seen fluids course, but others, do you know the meaning of vorticity? Curl of the. So now this vorticity, if I use omega for this, this is given as del cross V. Okay, and physically what it tells you is about the axis, how fast is the particle spinning. Okay, it's given by del cross V, and in some of the course you may have encountered a vorticity equation also. You may have seen it, I don't know, most of you should have seen it. It must have been done in the advanced fluid mechanics course. The vorticity equation, I'm not even going to write it now because I don't remember it and I'm just doing a qualitative discussion. This you get by taking a del cross of the velocity equation. And possibly we'll do this in homeworks or something soon. So you take a curl and you get this. Now in the vorticity equation, there is a term called vortex stretching, omega dot grad u. U is the velocity vector, so omega dot grad, let me use V. I've been using V here. So this omega dot grad V is called the vorticity stretching term, and this term is 0 for two-dimensional flows. If the flow has got only two components of velocity, Vx and Vy, and functions only of x and y, then you can check omega dot grad u will be 0. And I'll show that, and this must have been shown in the course where you did it. If you are not comfortable, you can discuss it with me after class. So, in turbulent flows, if the flow is two-dimensional, this vortex stretching term does not exist, and therefore vorticity essentially tends to die because of the absence of this term. And since there is a lot of mixing in the turbulent flows, so therefore vorticity has to be there. So therefore all turbulent flows will have three-dimensional vorticity fluctuations. So flows have to be three-dimensional. In two-dimensional, you'll come across most of the turbulent flows therefore have to be three-dimensional. The velocity will have all the three components, vorticity will have all the three components. So, and that is one of the features of the turbulent flows. Then another feature of the turbulent flows is that there is a high rate of dissipation, which means that turbulent flows are always dissipative. Now in a turbulent flow what happens is viscous stresses do deformation work, which increases internal energy at the expense of kinetic energy. That means the kinetic energy which is there, kinetic energy essentially comes from the velocity term. Half mv square is the kinetic energy. So there is something which is causing the motion, and that is getting converted to internal energy, which means eventually ends up heating up of the system. And this change of energy, we still have time, so I think we'll be able to sustain it through. So this change of internal energy, kinetic energy to internal energy is what we term as dissipation, and this is a very key feature of the turbulent flows, which means the flow will need some continuous supply of energy. If there is a turbulent flow and you leave it as it is, and this happens in what is called the grid turbulence. In wind tunnel, of course, wind tunnel has a different meaning in IIT Delhi as compared to scientific wind tunnel. So in wind tunnel, there is often a honeycomb and small flow comes in. And suppose if you do not have any source of kinetic energy, that means you just let the flow to decay, then what you will find is that turbulence will decay. But if you have a fan or something which is causing the flow, so then what will happen is energy will be constantly supplied to the flow, and then turbulence is sustained. But in the absence of that, if there is no energy source, then the flow will get basically will be dissipated and there will be no flow. We need a continuous supply of energy for a turbulence flow to be sustained. Now this could come, for example, if there is it could come from buoyancy. There is a heater in the room that is heating up the air, that continuously keeps on having, we keep on having motion because of that. So energy could be provided by that. But some source of energy would be needed for the flow to be maintained. Then I'll just finish soon. Turbulence is still, whatever we said, still a continuum phenomena, which means that scales in a turbulent flow or smallest scales in a turbulent flow, while they are much smaller than a laminar flow, but still they are much bigger than molecular scales. So therefore, these turbulence in turbulent flows, even the smallest scale will contain many molecular scales. So the continuum approach will be valid, and that's why the Navier-Stokes equations still tell us about turbulent flows. Had the flow been at a scale where the scales were equivalent to the molecular scales, then we could not have made this statement. And the last property which I would like to talk about and end with that is, what we find is that the flow has a very sensitive dependence to initial and boundary conditions. Now, has anyone read something about chaos? This is one of the characteristics of chaos, that you say chaos is always very sensitive to initial conditions. What do I mean by this? You have a flow, you close it, you start the flow again with the same initial condition and same boundary conditions. You will find, then what would you expect? The second flow should be the same as the first one. But if you look at the, let's say, velocity field and all, you will never find it will be reproduced. And the reason for that is because you'll never be able to start exactly from the same situation. You'll be able, when you start it again, there'll be some sort of epsilon variation from the condition where you started. And because the flow is sensitive to initial condition, you'll never get the same readings again. Okay, so that is the meaning of sensitive dependence to initial condition, and that is very much a feature of turbulent flows.
Sir, the initial condition part I understand.
हाँ
Like the butterfly.
हाँ बाउंड्री कंडीशन, बाउंड्री कंडीशन में यही है कि सपोज अगर कहीं बाउंड्री कंडीशन तुमने कुछ ओमेगा फ्लैपिंग दी है, if your boundary condition is that the plate is moving with some velocity, so now that, or oscillating, so maybe that oscillation will not be exactly the same as, or yeah, otherwise you are right that in boundary conditions it would be the same. See, or maybe you talk of flow in a pipe, then of course assuming that nothing has happened, then the boundary condition will stay the same. But in the boundary conditions you also give the inlet condition. Inlet condition is on velocity. So in given that velocity, there may be some fluctuation, there may be some epsilon variation. So pressure fluctuations could be there if they are there in the boundary conditions. So boundary condition need not only be geometry. At that geometry, what is the velocity? Of course, if it is a solid boundary, velocity has to be 0. But in the inlet and outflow conditions, that could change. Okay, I think at this I'll probably stop here, and we'll continue from this in the next class. So things will continue like this for some time, but then we will get on to the equations and